Hi there, welcome to this video on hypothesis testing. It is the chapter in the Year 1 Stats section of Maths A-Level, looking at hypothesis testing on the binomial distribution. Now there's a booklet that you can download that goes with these slides that you can fill in as you go along. I'll put a link to that file in the description so you can use that to make some notes which will help for your future revision. So let's get started. So let's get a flavour of what a hypothesis test is and have a look at this question. We're told that 10% of the world's population are left-handed. So that is a calculation done on the entire population, and it's not a statistic. A statistic is something you calculate from a sample. So on holiday in Hawaii, somebody wants to establish whether the proportion of left-handed people is greater than that of the rest of the world. Now, if we thought it was the same as the rest of the world, we could calculate 10% of a sample of 20 people is going to be 2. Now, suppose we've got 5 people in our sample that are left-handed and we're only expecting 2. So what we do is we form two hypotheses. H0 is called the null hypothesis. Now that is always on the basis of whatever's going on currently in the entire population. So the probability of left-handed is 0.1. Now our alternative hypothesis we get from the wording of the question, and we suspect that in Hawaii it is greater than 0.1. So P is bigger than 0.1. Now, because we're only going to be testing at one end, this is going to be a one-tail test. Now, it's a binomial distribution because you're either left-handed or you are not. And what we do is we look at the probability of X being greater or equal to 5, so 5 being the least amount of left-handed, what's the probability of that happening? And we assume that H0 is true. So we do this on the basis that X is binomially distributed with a sample of 20 and a probability of success is 0.1. So on the basis of that, when we're going to be expecting 2, what's the probability of 5 or more? Now, if you do that on your calculator, it comes out to be 0.0432. Now, putting that as a percentage, that's 4.32%. And you compare that with the significance level, which is given here in the question 5%, and that is less than 5%. So on the basis that we thought there was 2, we actually got 5, and the chances of that happening is so small and sufficiently lower than the significance level, that's going to cause us to conclude that the proportion of people who are left-handed in Hawaii is greater than the world's proportion. And in this case, we would be rejecting the null hypothesis in favour for the alternative hypothesis. So that is the gist of hypothesis testing. We have some hypotheses, and the default position is you start with whatever's going on in the population. We've got an idea that it might be higher or lower than that population default. So we collect some data and we see what's happening with the data. Now, whenever you've got a sample, that's going to be our test statistic because you get a statistic from a sample. If the data is sufficiently unlikely to have emerged just by chance, we conclude the alternative hypothesis is correct. So if in our data it turns out that it's so extreme from what we were expecting and it's less than that significance level, then we reject the null hypothesis in favour for the alternative hypothesis. So let's have a look at another question. Suppose I've got a coin, I'm going to throw it 10 times. For what number of heads might you conclude that the coin is biased towards heads? So it's either heads or tails, so you're going to have a binomial distribution, and you would let X be the number of heads that turned up. Now, you'd expect if we threw it 10 times that you would get 5 of each, and that's theoretical, but would that happen in real life? How many heads need to show up for us to conclude that it was actually biased? So we set out the hypotheses. Is the coin biased? And then we say that we've got the binomial distribution, so N and P. The default position is the H0, the null hypothesis that we have got 0.5, the probability of getting heads. That's saying that the coin is fair. The alternative hypothesis is that it's going to be biased towards heads. So you would write that as H0 P is equal to 0.5 and H1 P is greater than 0.5. So again, we're just doing a one-tail test. Now, based on the fact that you would just be expecting 5 heads, what's the probability of X being bigger or equal to 9? Now, when you're doing binomial on your calculator, you have to use binomial CD, so you have to scroll over to the next page, and then you have to do a 1 minus because it's always to the left. So this is going to be 1 minus the probability that X is less than or equal to 8, because you're either up to 8 or above one or the other, so you can just do 1 minus, and this actually comes out to be 0.0107. And then if we have a look at the probability that X is bigger than or equal to 8, so that would include this one as well, that would be 1 minus the probability of X being less than or equal to 7, which on a calculator is 0.0547. Now you compare these two answers to the significance level. Now usually the significance level is about 5%, and if it was 5% in this question, we can see that the probability of getting 8 or more is obviously higher because that's nearer to what we're actually expecting, and that would be in the allowed region for us to carry on believing that the coin was fair. But if we'd actually got 9 heads and got this result, because the probability of that happening is so low based on the fact that we were expecting 5 heads, we would then have evidence to reject the null hypothesis in favor for the alternative hypothesis. So in this example, we've got an election candidate believing that she's got the support of 40% in a particular town, and a researcher wants to test at the 5% level to see whether the candidate is overestimating. So the researcher thinks that she doesn't have as much as 40%, she thinks that's above, so she actually thinks that the support is less than that. The researcher has asked 20 people and found that only 3 support the candidate. Now, if we thought the candidate was correct, 40% of the sample of 20 would be 8, and only 3 people have said they support the candidate. So the test statistic that we're testing against is the number of people who say they support the candidate, and we can write here that X is binomially distributed. We've got a sample of 20 people, and we can write P being the support, the probability that somebody supports, and that's going to be the success. And then our hypothesis is that H0 is P is equal to 0.4. That's what the candidate believes. And because we think it's an overestimate, we actually think that it is less than that. So then we could write, assuming H0 is true, then X would be binomially distributed with 20 and 0.4. Now, on that basis, we can then calculate what is the probability of X being less than or equal to 3. And we can compare that answer to the 5%. So let's just run through properly how you should set out a hypothesis test question, and these 4 points are what you're going to get the marks for. So we've got John throwing a coin 8 times and it comes up heads 6, and he claims that the coin is biased towards heads. With a significance level of 5%, we're going to test his claim. So first of all, you have to define the test statistic, X being the number of heads and P being the probability of heads, and it's going to be a binomial distribution because you're either either heads or you're not, and we have got the fact that he's tossed the coin 8 times. So writing our hypothesis, the null hypothesis is on the basis that we think the coin is fair. That's what currently goes on with coins in the population. So P is equal to 0.5. We think it's biased towards heads, so we think the probability of getting a head is bigger than 0.5. So this is a one-tailed test. And then we're going to assume that H0 is true, and that's on the basis that we think the coin is fair. We can now say that X is binomially distributed with 8 and the 0.5. And what is the probability of us getting 6 or more? Now, if we threw it 8 times and the coin was fair, we'd expect 4 times to come up heads. What is the probability on that basis that we've actually got 6? So it's going to be 0.1445. Now you compare that answer with the significance level, and it's higher than the 5%, so this is insufficient evidence to reject H0. The coin is not biased. If the probability of getting 6 or more was below the 5%, that would give us the evidence to reject H0, and we would think the coin was biased. But because that 14.45 is bigger than the 5%, there's no evidence to suggest that this coin is biased. So we've already seen with this example of John throwing his coin, he throws it 8 times. What would be the most amount of heads that's going to turn up to lead us to reject the null hypothesis at the 5% level? So when we did the probability of X being bigger than or equal to 6, we did 1 minus the probability of X being less than or equal to 5. Now you do that on your calculators, or you can look it up in the table. Everything up to 5 on this cumulative, C stands for cumulative there, binomial table. It's going to be 1 minus 0.8555, and that gave us the 0.1445, which is the 14.45%, and that was above the 5%, so that is still within the realms of possibility that he could get 6 heads, even though in 8 throws we're only expecting 4. The probability of 6 happening on the basis that we're expecting 4 is not below the significance level. So what if we went to the next one down and did the probability that X was bigger or equal to 7? So that would be 1 minus the probability of X being less than or equal to 6. 1 minus 0.9648, and that comes to 0.0352. So as a percentage, that's 3.52, which is less than the 5%. So the probability of that happening is so low, considering that we were expecting 4 heads. It's in what we call the critical region, and that is the region where you get so many heads you are going to reject the fact that you think that the coin was fair in favor for you thinking it's biased towards heads. So the critical region in this case would be if we have 7 or even 8 heads, then we would be thinking that this coin is biased. So where to look to find these critical regions? You can just use your calculator and just put the values in and try and find the probability that's going to work, but it's easier to just use the tables. The tables are cumulative as we go down the list, so you just need to find the right N and P in the table. So say we were throwing a coin 5 times, we want to establish where is the critical region that's biased towards heads. So you look down the table to see where it goes past the 0.95, because we're going to be doing 1 minus 0.9688, and that's going to give me a value that's going to be less than the 5%, because that's our significance level, and therefore I'd be doing 1 minus the probability of X all the way up to 4, which would actually be the critical region of X being bigger than 5. So you go to where it's just gone past, but then it's the one after, because you're going to be doing the 1 minus. So if I'm throwing the coin now 10 times, where's going to be my critical region? You're going to run your eyes down the list and see where does it go past the 0.95. So you're going to do 1 minus 0.9893. That would give you a value less than 5. So the actual probability that you're calculating is 1 minus everything up to and including 8, which is actually the probability of x being bigger than 9. So 9 is going to be our critical region. Now in the next one, if we're looking at throwing a coin 10 times again, but biased towards tails, that means that we want less heads. So we're at the other end of the tail, and here you're just looking where it just goes before the 5, because you're not going to be doing a 1 minus. So here, going up to the up to 1, you see if we go to 2, that's going to be bigger than 5, so this would be the probability that x would be less than or equal to 1. That's going to be less than our 5% significance level, so x would be less than 1. So at the negative tail, the lower tail, we just use the value that goes under the significance, whereas in the other tail, you need to go just after. If you're asked to find the actual significance level, well, you look to see the first value in the critical region. We've already seen that this is going to be 7 when we're throwing this coin 8 times. So the actual level of significance is going to be the first point that we're in the critical region that's going to be less than the 5%. So here, the actual significance level would be 3.52%. When you're looking at doing a two-tailed test, you just know that the coin is biased, but you don't know in either way. And that comes again from the wording of the question. So if we're looking at whether this coin is biased, we don't know which way. We're testing at the 5% level. What you do with the 5%, you have to half it at either end. So at the negative tail, looking at the lower level down the list, you're looking now for where it goes up to 2.5, which is 0.025, and you can see if we get this one's too high, so at the negative level it's going to be just 0 heads. At the positive tail at the other end, we can see we're looking for where it just goes past 0.975 now, taking that 2.5 away. So that only happens here, so we'd be doing 1 minus everything up to 7, which would mean we'd have a positive tail critical region of everything equal to 8. So both extreme ends are the only way that we would conclude that this coin was biased. Another word to look out for with hypothesis testing is the word close. So we've got a binomial distribution, and we can see from the alternative hypothesis that we're doing a two-tailed test. When you're doing a two-tailed test, you're going to share that significance level at either tail. So we're looking for 1%, and it's asking us to find the critical region in each tail being as close, and that is the 1% as a decimal. So in the lower tail, we're just looking for everything before the 1%, and we can see these through the table here, these decimals as percentages. That would be 0.47%, and that would definitely be in our critical region because that's less than the 1%. The one after is going to be 1.6%. Now 0.47 is 0.53 away from 1, and 1.6 is 0.6 over. So which one is the closest? It's going to be the one that is in the critical region because it's less than the 1%. So at the lower tail, we've got 0 to 3. Now in the upper tail, you're going to look for where it goes past 0.99 because that complements to the 1%. So you can see here, we're going to be looking at the 17. So the probability that x would be greater than or equal to 18 would be 1 minus the probability of x less than or equal to 17. And when we do 1 minus the 0.9953, that gives us 0.0047, which again is going to be 0.47. But if we look at the one above and did 1 minus the 0.9884, that would give us 0.0116. Now moving the decimal place and putting those two as percentages, you can see this is going to be 1.16%, against 0.47%. So the 16, although it's only 0.16 above 1%, it's not in the critical region, but because it is closer than the one before, we are going to allow that as well. So if we're doing 1 minus the 16, that means everything not including the 16. So it's going to be 17 less than x less than 40 is going to be our critical region at the upper tail because of this word close. Now, what is the actual significance level for part B? We're just going to add up those decimals and get 0.0163, which as a percentage is 1.63%. So even though we've gone a little bit over with our upper tail, we're still less than the 2%, and we've been allowed to go out of the critical region because of that word close. Not really referred to as the p-value in the textbook, but I have seen some exam questions where they refer to the p-value. So the p-value is just the probability that's been worked out for you already. So if the p-value is 0.03, all we have to do in this question is compare it to that significance level, and it's less than the significance level, so that would suggest and give us evidence to be rejecting the null hypothesis in favour for the alternative hypothesis. So here's a further example. We've got some treatment for a particular disease has currently 2/5 probability of being successful, and a doctor has got a new drug and believes that with the new drug 11 out of 20 people have been cured, and we're being asked to test at the 5% level whether this new drug does represent an improvement. So 2/5 of 20, we would be expecting 8 people, and with this new drug 11 people have been cured. So from the wording of the question, it's going to be a one-tail test, but first of all we need to define our test statistic. You're either cured or you're not, so it's going to be binomial. You don't fill in the probability until you've stated your hypotheses. The null hypothesis is the 0.4. That's the default position of what currently is the success rate for this disease. The doctor thinks there's improvement. It's a one-tail test. Then we can say that we're going to assume that H0 is true. So we can fill in that the probability is the 0.4. And we're going to test what is the probability of 11 or more. So you're going to do 1 minus everything up to 10. That would give you the same as probability of 11 or more, and that comes out to be 0.1275. Now the 0.1275 is 12.75%, which is bigger than the 5% significance level. So this gives us not enough evidence to reject the H0. Even though we're expecting 8 to be cured, the fact that 11 is still within the realms of possibility, it's not so low that it's less than our significance level. So there's no evidence to suggest that this new drug is better than the old one. Here's a question for you to have a go at. So you can pause the video and have a go at this one. I'm going to go through the answers now. So we've got a student taking a multiple choice test. The test has 10 questions. Each question has 5 possible answers. This student gets 4 correct. The teacher claims that she was guessing. Do a one-tail test at the 5% level and see whether we can reject or support the teacher's claim. Now, if there's 5 possible answers for each question, if she was guessing, we would think she would just get 1 in 5 correct. And if there was 10 questions, that would lead us to think that if she was guessing, there would be 2 correct. So you can either get a question right or wrong. So this is why it's going to be a binomial distribution. We've got 10 questions. Probability of success is P. Now we're going to state our hypotheses. So the null hypothesis, if she was guessing, the probability of success is going to be 0.2 because there's 5 possible answers. So you're going to get 1/5 of the questions right from guessing. And then our alternative hypothesis, if she wasn't guessing, if she's actually done some revision, then we would think that the probability of success would be 0.2. So once we've stated those, we can assume that H0 is true. Assuming the null hypothesis, then X would be binomial distributed with a probability of success of 0.2. And then because she's actually got 4 correct, assuming that she was guessing, therefore the probability of success would be 0.2, what is the probability of x being greater or equal to 4? Well, this is to the right, and we need to use our calculators or the tables which go from the left. So we need to do 1 minus the probability that x is less than or equal to 3. So this is 1 minus 0.8791, which is 0.1209. Now putting that as a percentage, that's 12.09%, which is bigger than the 5%. So in order for her to be not guessing, we would have to have a probability of that many right to be less than the 5%. So this, not being in the critical region, does support the teacher's claim. So we would say this provides, therefore, there's evidence to support or accept H0, and teacher's claim is supported. So you get 2 marks for doing that conclusion, saying what you're going to accept, reject, and then saying how that fits in with the context of the question as well. Now, the other thing that you get full marks for that, but the other thing you could do, instead of saying what's happened here, just find what the critical region is. Now, if she got 1 more correct, say the probability of x being greater or equal to 5, so 1 minus up to 4, that turns out to be 0.0328. So as a percentage, that would be 3.28, which is less than the 5%. So had she got 5 or more correct, so 1 more correct, then the teacher's claim would not be supported. So that's the other way round to think about it. Here's another question on two-tailed test, and when we've got a two-tailed test, we're going to half that significance level at either tail. So we've got Enrico's restaurant, where the ratio of non-veg to veg is 2 to 1. So every 3 people, 1 person orders vegetarian. In Manuel's restaurant, we've got 10 people and only 1 person has ordered a vegetarian meal. So already we're thinking that Manuel's restaurant has a lower ratio of people ordering vegetarian, but we're going to test at the 5% level to see whether or not Manuel's restaurant is different. So it's this word different that means that we're doing a two-tailed test. Even though what's happened in this sample in Manuel's restaurant looks like it is less, we're still going to do a two-tailed test because of that word different. So the proportion of people eating vegetarian in Enrico's is 1/3. So that's like our default position. So we're going to let H0 equal 1/3 and H1, because we're doing a two-tailed test, to not equal 1/3. So if H0 is true, the null hypothesis is true, we're going to assume 10 and 1/3. And then what's the probability of x being less than 1 in our sample of 10? So that comes out to be 0.104, which as a percentage is 10.4%, which is going to be bigger than our 2.5%. So you can just leave it there as decimals. Therefore, insufficient evidence to reject H0. There's no evidence that the proportion of veg meals at Manuel's is different to Enrico's. Here's another question to test your understanding, so you can pause the video and have a go at it. I'm going to go through the answers now. So a teacher thinks that 20% of the pupils read the Dino. He chooses a random sample of 20 and he finds that 9 of them read the Dino. Now, if there was 20% of our 20 people, that would actually be 4 people, and already he's found 9 in this particular sample, so it looks like we might have the original percentage wrong. We're testing at the 5% level and to see whether there's evidence that the percentage of pupils that read the Dino is different. Now this word different means that we're going to do a two-tailed test. So you always decide what type of test it is from the wording of the question. State your hypotheses clearly, and then we've got part 2 to do as well. So here is the mark scheme. So we're going to be saying that X is binomial distributed first with a sample of 20 and a probability of P. Our hypotheses are that the P is 0.2, that's the current default 20%, and because it's a two-tailed test, our alternative hypothesis is that P is not equal to 0.2. And then we would be assuming that H0 is true. Then what is the probability of having more than 9? Well, that's going to be 1 minus up to 8, which turns out to be 0.01. So that is going to be less than the 2.5%, because that would be 1% is less than the 2.5% because we're sharing the 5% at either end. So reading 9 or more is giving us some evidence to say that the percent of pupils who read the DINO is not, because we are in the critical region. Now in part 2, state all the possible numbers of pupils that read the DINO from the sample of 20 that will make the test significant at the 5% level. So we're going to say that anybody reading 9 or more, so how many could we have in total? Well, there's 20 people in our sample, so 9 or more, but at the lower end, if no people read the DINO, that would also be in the critical region. Now this notation here with the square brackets is interval notation, and that just means 9 less than or equal to x less than or equal to 20 with those square brackets. Thank you so much for watching. If you're still with me at this point, hopefully that's helped with your understanding of hypothesis testing. Do like and subscribe and check out other videos on the channel, and good luck with all your exams if you're taking them this year.